we're going to be looking at atomic structure and the periodic table. There is a key that you need to be just mindful of as we're going through this. Anything in green is content you will be assessed on, while if it's greyed out, that is content not in your exam. Every single section of today's session will have this key in the bottom right hand side. We've got Combined Science Foundation, Combined Science Higher, Separate Science Foundation and Separate Science Higher. When the content is green, it means it is on your specification. It could come up in your exam. If it's greyed out, it means that actually this isn't in your exam. You don't need to worry. There is a small section at the end of this video which will just be for Separate Science Higher and Separate Science Foundation only. And so you'll kind of notice that as we go further through this. To start with then, we're going to start with atoms, elements and compounds because it's really important we've got our key phrases set and sorted and happy to use them in interpretation questions, but also just using it in our language within exam questions. So atoms, first of all, are the basic building block of matter. And we'll look at this as we progress through the topic, but these are made up of a central nucleus with electrons surrounding outside of them. And they make up elements, they make up compounds, they make up molecules. But atoms are singular. Molecules, on the other hand, are now any substance that is made up of two or more atoms chemically bonded together. It could be two of the same atoms, in which case it's an element, or it could be different atoms, which means we'd have a compound. But a molecule is more than one atom or two atoms or more chemically bonded together. Every element that exists is found on the periodic table. So every atom of every element is represented by its own chemical symbol, and you'll be given a copy of a periodic table in your exams. There are roughly around 100 of these elements on the periodic table, but if it's on this periodic table, it means it will be an element. We also have compounds, and these are typically formed by chemical reactions, but compounds are substances in which we've got two or more different types of atoms chemically bonded together. And that whole idea around chemistry is that generally what we'll find is that in any chemical reaction, we will make new substances, and there will often be an energy change. So there might be a temperature increase or a temperature decrease. When we look at compounds, they will have specific formulas because their elements will be, or the atoms within them will be in fixed proportions. So for example, water's formula is H2O because it has two hydrogens chemically bonded to one oxygen. So when we're looking at compounds, we're going to have a lot of chemical symbols and formulas throughout. If we do want to separate out the different types of atoms within our compound, you can only do that by chemical reaction because here those atoms are chemically bonded together. Mixtures are now made up of different substances that are not chemically bonded together. So here we see a mixture made up of one compound, which is here the two reds attached to the black, and we have two separate kinds of elements. So here this is actually just an atom of a kind of element, and here we've got a molecule of another element. Now the chemical properties of everything in this mixture remains unchanged, so each of these molecules keeps its own distinctive properties. Now what this does mean is they can be separated through different processes. There doesn't have to be a chemical reaction here. We're not making anything new when we go to separate these mixtures. There are different separation techniques that are going to link into quite a few different areas of the specification, and so these will be revisited at different points within your papers. But we've got filtration, we also have distillation, so we can have this as simple, or we can have fractional distillation. There's also chromatography as well as crystallization. So there's a wide different range of different separation techniques. Now fractional distillation and chromatography tends to get more of a feature in your paper 2, while crystallization, filtration in particular, will tend to be more in your paper 1. So with filtration, this method is going to be used where we pass a substance through a piece of filter paper. The idea is that the insoluble substances are removed and trapped by the filter paper, and we'll call this a residue, while anything that's soluble, dissolved in the solvent, will pass through below into, in this case, a conical flask. So filtration is used to separate insoluble substances from a liquid by using filter paper. And sand from water might be a good example of doing this. Later on, when you look at chemical changes and making salts, you use filtration to remove insoluble bases from a solution. Another method that we use, and we use this when we're making salts also, is crystallization. Now, this involves evaporating from a solution to actually reduce the volume of that solution, and what you will normally do is extract the solute that was dissolved into it. So with this, we'll have a Bunsen burner heating normally beaker of water that we refer to as a water bath, with, in this case, our evaporating basin on top, and this is to heat that gently. So the purpose of crystallization will be to separate a soluble solid from its solution by removing the liquid it's dissolved in. And you'll do this, for example, we can separate sodium chloride, so salt, from seawater doing this, or again in chemical changes later on in paper 1, you can use this method to remove the water that you formed in the neutralization reaction when you've made salts. Simple distillation involves evaporating a liquid and then cooling the vapor and collecting its condensate. Now this can be used to separate a liquid from a solution. So if, for example, I've got salty water and I'm after the water in the salty solution, I can evaporate the liquid, get it to go down through this condenser that is cool, and then actually turn that gas back into a liquid and collect it. That should be their pure water. So this is our way of getting like water from salty water. Fractional distillation will have more of an appearance on your paper too, but this now involves the heating and cooling of substances that separate because of the fact they've got different boiling points. And so in paper 2, you'll look at this with extraction and separation of crude oil. So this involves the separation of a mixture into different fractions. And with this, they will separate according to their melting and their boiling points. Now we use this specifically in paper 2 when we separate crude oils, but could also be used, for example, to separate a solution that maybe contains alcohol and water. Chromatography also has a bigger feature on your paper too, but gets mentioned early on here in the specification. Now this is used to separate mixtures of coloured compounds, and predominantly we can use this to separate inks and dyes. This works because of the fact that the chromatography has a mobile phase that the substance dissolves into, and it moves up the stationary phase, the chromatography paper. The next section of the spec then is knowing about how the model of the atom changed. Now this ties into physics also, as it's also content that comes up there. Now here, ideas about the model of atom have changed, and it's always down to the discovery of some new evidence that leads to us having to change this. So with particles, we started off with Dalton, claiming that atoms were tiny spheres that could not be divided into anything smaller. The reason for this is that we knew there was matter, but not a lot else. Electrons, protons, neutrons had not been discovered. J.J. Thomson then modified this model when the electron was discovered. So what he did was went on to propose the plum pudding model. So in this model, it's the idea that we've got a ball of positive charge with negative electrons randomly just embedded within it. So the model changed due to the discovery of the electron. Next came the alpha particle scattering experiment, which now started to prove the existence of protons. And this was done by Rutherford. He got a really thin sheet of gold and he fired small particles known as alpha particles at this sheet of gold. Now what he found was that the majority of those alpha particles went straight through the sheet of gold, which was his evidence that the atom must mostly be empty space. So his observation was they went straight through. What that proved was the atom was mainly empty space. Now, some of them did deflect. So what this meant is they went through, but they came out at an angle. Now, Rutherford knew the alpha particle was positive, and so the deflection meant that actually the nucleus, whatever was in the centre of the atom, must be positive, and that's where the discovery of the proton has come in. Some of them did kind of deflect back quite strongly, and that provided evidence that there must be a small but concentrated mass in the centre of the atom to actually get very few to completely come back. Now this might be a 6 marker. Here, structure your answer to say what was observed. So for example, the atoms passed straight through and what that meant. So the atom was a mainly empty space, or that the alpha particles were deflected. This proved the nucleus was positive. So observation with what that meant for the structure of the atom. So those observations meant that the atom structure had to be changed. And that's where we've ended up now with electrons just around the outside somewhere. And we now have a positive nucleus containing protons in the centre of the atom. A common question that comes up is you might be asked also to compare the nuclear model, so Rutherford's model, to J.J. Thomson's plum pudding. The similarities is they both contain electrons and they both are missing neutrons. However, the difference is the position of those electrons. With Rutherford's model, they're now orbiting around the outside, and we've gone from having a big solid ball from J.J. Thomson to now having a very small nucleus containing protons with a large empty space in between. The mark, though, that most students forget to mention as a similarity is the lack of neutrons. Next came Niels Bohr. Now he adapted the model even further by suggesting that the electrons now orbit the nucleus at specific distances. So he is responsible for the rules around the fact that we have 2 electrons in the first shell and 8 in the next. James Chadwick then went on to prove the existence of the neutron. So only at this point have we now got all 3 structures of the atom in place, those protons, neutrons and electrons. So our general structure of the atom then is very much a GCSE level where James Chadwick finished. We've got a nucleus in the centre containing protons and neutrons and electrons around the outside. The masses of these particles, protons and neutrons, weigh the same as each other, so they're given a relative mass of 1, while electrons are approximately 1 over 1840 smaller than a proton or neutron. The charges though, protons have a positive charge while neutrons have a neutral. Electrons have a negative charge. So the protons are in that nucleus with a mass of 1 and a charge of +1. Neutrons also found in that nucleus have a mass also of 1 but no charge. Electrons are in electron shells around the outside with a very small mass, you could say tiny. We'll try and volunteer the actual comparison, but very small for AQA is often enough. And the charge is going to be -1. Now the atoms are neutral. This is a very common 2-mark question when you're asked to explain why. Now it's down to the rule around the number of protons and electrons. Every atom has its own atomic number, and this is the number of protons that it contains. Now for an atom, the rule is that they have the same number of electrons and the same number of protons. So whatever number of protons you've got in an atom, you have the same number of electrons. But protons have a positive charge while electrons have a negative. So overall, there's no electric charge, giving you a neutral atom. A general fact recalls that are really useful to put on flashcards Atoms have a radius of about 0.1 nanometers. There have been questions in the past where you're asked to predict the size of a molecule containing two atoms. Well, 0.2 nanometers wide, down to the fact we'd have two joined together. The radius of a nucleus is actually 1/10,000th of the size of that. I'd really recommend just have in mind that atoms are 10 to the power minus 10 meters big, while the nucleus tends to be 10 to the power minus 4 meters big. And what we find is pretty much most of that mass is inside of the nucleus of that atom. Now that leads us on to mass number. This is our total number of protons and neutrons in an atom. And what we can find is that sometimes atoms have got a mass number that's not a whole number, and it's down to isotopes. Again, very common thing to be asked to define, but isotopes have got the same atomic number, so they're elements of the same atom with the same number of protons, but a different number of neutrons. So relative atomic mass is the average mass that takes into account the abundance of all of these isotopes. Protons and neutrons both have a mass of 1. And so if we look, here we've got carbon with a mass number of 12. If carbon has got an atomic number of 6 and a mass of 12, that must mean it has 6 protons and must also have 6 neutrons to give it a total mass of 12. If we look at chlorine though, this now has a mass of 35.5, and it's not because it's got half a neutron in there. So this is because of the fact that we've taken that average from the isotopes. So here it's down to that combination that some chlorines will have more neutrons than others, and that will give us this overall average that's not a whole number. So with these isotopes, they are atoms that are of the same element with the same number of protons but a different number of neutrons. And you might be asked in the exam to figure out the actual mass number or percentage abundance of an isotope. So with this, you can find the actual mass of an isotope using its mass numbers and abundances. And you can, for normally 2 or 3 marks, be asked to do this. So to do it, you need to multiply each mass by its percentage and add those masses together. So, for example, we'll do 6 times 7 plus 7 times 93, which gives us a mass currently of 693. Divide that by 100, and our mass of this element will be 6.93. Notice it's a value that is between the mass numbers that we've been given. So you times your mass by percentage abundance, add them together and divide by 100. And it's a really common exam style question that comes up. With our electronic structure, again, very common question to come up. This is a way in which electrons are arranged in an atom. And we need to know the rule that 2 electrons are found in the first shell, then 8, and then another 8. So for argon, for example, is 288. Moving on to the periodic table. This shows us all of the elements that exist, and elements today on the periodic table are arranged in atomic number. So if we notice, it's going 5, 6, 7, 8, 9, 10. So we're increasing by 1. Each of these have 1 more proton than the one before it. Now, elements with similar properties are found in columns together, and these are known as groups. And it's called a periodic table because we do see similar properties occurring in regular patterns. Where an element is on this periodic table tells us a lot about its structure. So, for example, if something is in period or row 2, that tells us it's got 2 shells. If it's in group 7, that will tell us that it's got 7 electrons in its last shell. So if we look, hydrogen and helium are in different groups, but they are both in period 1. They're in the first row of the periodic table. They both have 1 shell. Lithium, beryllium, fluorine and neon are all in period 2, and they all have 2 shells. When we look at the groups, here's our group 1 elements. they all have one electron in their outer shell. This must be in period 2 because it's got 2 shells, while potassium over here would be in period 4 because it's got 4 shells. So the group it's in tells us how many electrons are in its last shell. Here, for example, we've got our halogens, so fluorine and chlorine, both in group 7 because they both have 7 electrons in the outermost shell. And it does mean because of this, they behave in really similar ways. Now, we'll talk about our noble gases later, but noble gases are slightly different. They all have full outermost shells. A common mistake is people might say, oh, they're all in group 0 because they all have 8 electrons in their last shell. Now, that's not true because of helium. What they have is that they all have full outermost shells. The periodic table has, like the model of the atom, been a work in progress. So, in the past, the atoms on the periodic table were arranged in order of atomic weight. But the problems with this is that it was incomplete and some elements ended up in the wrong groups where their properties didn't match. So, for example, oxygen and iron, 2 very different elements, should not be in the same group. Now, Mendeleev made changes to this periodic table. So, in the early periodic table, it was incomplete, and so Mendeleev left gaps. Some elements in the early periodic table were in the wrong groups, and so what he did was actually occasionally he found that he had to change their order based on atomic weight. So he put them in weight order, but then made a couple of swaps to make sure that all the properties fitted. So he also placed these elements in atomic weight, but made a couple of adjustments. Today, our periodic table is in order of atomic number. So over time, his ideas were accepted because he left gaps and elements were discovered that fitted those gaps. But also, when Chadwick came up with neutrons and their existence, we learned about isotopes, and it started to explain why actually changing the order of some elements worked. But today, it's in order of atomic number. It's a common question that comes up. How did Mendeleev arrange it? Atomic weight. How is it ordered today? Atomic number. On the periodic table, we've got metals and non-metals. Now, there's loads of different examples of some metals, and on non-metals, our halogens are a good kind of group to go to here. When we want to find out if something's metal or not, generally metals are found bottom and towards the left-hand side, while non-metals are found up here to the right, up and to the right. We can use this dividing line here as a rough guide around it. So, as a rough rule of thumb, on the left-hand side of this line, you're looking at metals. On the right, you'll have your non-metals. And the way to kind of remember this is the idea that aluminium is under the stairs. Now, metals are elements that will react to form a positive ion, and they're found at the left and towards the bottom, while non-metals will form negative ions and are found on the right and towards the top. Now, the elements in group 0 are known as the noble gases. As you go down, their boiling point increases. That's typically actually a trend for most elements in the periodic table. And it's because the molecule or the atom here is getting bigger, so forces of attraction getting larger. And we'll touch on that in structure and bonding. These group 0 elements, however, are all very unreactive because when we draw their electron configuration, they've all got full outermost shells. And so as a result, they're incredibly stable. But just be aware, just in the event they ask you what they all have in common, it is full outermost shells. Don't put a number on it. Group 1 are otherwise known as the alkali metals. We've got lithium, sodium, potassium that are commonly used here. Now, because they all have similar electron configurations, means that their chemical properties are very similar, and you might be asked to describe their reactions or write equations for these. So, first of all, when alkali metals react with air, this happens incredibly quickly. They'll go from shiny to dull, and as a word equation, lithium plus oxygen will make lithium oxide. and this will be our balanced symbol equation for this. But actually, if we notice, for any of our alkali metals, they all react in the same way. And notice the only thing that's changing here is the symbol. And I'd say once you've learned one, you've learned all of them. We've also got the alkali metals, and they react with water, and they do so quite vigorously. Now, there are some common observations when any alkali metal in a lab is added. They'll typically float on the surface, there'll be loads of fizzing, and what we'll see if we've got universal indicator in there is it'll turn purple, and that's where this phrase of alkali metals coming up. Typically also the metal will melt into a ball until it eventually just disappears. So they all react pretty quickly, but the way in which they react, the word equation and symbol is the same for each. So if we've got lithium and water making lithium hydroxide and hydrogen, here's our balanced symbol equation for this. But if we notice, there's my lithium, sodium, all that's happened is I swap out lithium for sodium and swap the symbols. Everything else is exactly the same. So again, once you've learned one equation for the alkali metals for the reactions with water, you've technically learned all of them, as long as you're happy to swap out that name. Now, as we go down this group, what we find is the reaction gets more vigorous, because lithium is the least reactive, and as we go down, we've got increasing reactivity. Now, lithium reacts pretty quickly, but actually, this will get quicker and quicker as we go down the group. So, when any alkali metal, and by this I mean lithium, sodium, potassium, the ones you can do in a lab, when they react with water, you'll see effervescence, so fizzing. The metal will melt into a ball, it will float on the surface and move around, and eventually the metal will disappear when it's fully reacted. It will be slower for lithium than it is for sodium, and it'll be faster again for potassium. But sodium will have more bubbling, it will melt into the ball faster, and you might even see a yellow flame. But when you get to potassium, there is one difference in that you might and you will see a lilac flame when potassium reacts. So it will react faster, and it will react by actually burning purple. Be prepared in your exam to explain why the reactivity of group 1 changes. So for 1 mark, as we go down the group, it gets more reactive. This is because as we go down the group, the atom is becoming larger, and so the outermost electrons are further away from the nucleus. There is less what we call nuclear shielding. Now, what this means is that the attraction between the outermost electron and the nucleus is less, and so therefore the outermost electron is more easily lost. The halogens are now across in our group 7, and these are a group of non-metals that are actually pretty toxic. And if you ever spot halogens being used in an experiment, as a safety precaution, mention a fume cupboard. But they all are in group 7, so they have 7 electrons in the outermost shell. We've got fluorine, first of all, right at the top, and this one is most reactive. It's yellow, and it's a yellow gas at room temperature. It's, as I've said, the most reactive out of the lot, and because it's the smallest molecule, it's got the lowest melting and boiling point out of all of these, and it's also low density. Chlorine is now a green gas at room temperature, so they get darker as we go down this group. They're less reactive than fluorine, but are more reactive than the other halogens, so the reactivity will decrease down this group. But it does, because it's slightly bigger, have a higher melting point than fluorine, and it will be more dense. By the time we get to bromine, this is now at room temperature a reddy brown liquid. It's the only halogen that's a liquid at room temperature, and when it evaporates, it forms like a reddish brown vapour. Iodine will be a dark grey solid at room temperature, but as a weird kind of state change, when we heat it, it turns straight from a solid into a gas, which we call sublimation, and turns into a purple vapour. Now, astatine, there have been questions in the past asking for predictions around its colour. The main idea here is that they're getting darker as we go down. So astenine, we haven't actually really seen it, it's quite rare, but it's a safe prediction. It's going to be a solid and dark black at room temperature, and same for tennessine. So as we go down this group, the melting and boiling points are going to increase because the molecules are getting larger, but the reactivity is going down and they will get more dense. One key bit for the halogens is that they will all form diatomic molecules. So what that means is that the molecule for fluorine will have the formula F2. All the atoms pair up. So fluorine will be F2 and it'll be a pale yellow gas. Chlorine, notice, Cl2, now our green gas. Bromine, Br2, our brownie, like reddy orangey liquid. While iodine will be I2, and this will now be our grey solid that when warmed will turn into a purple vapour. It's also brown when a liquid, so if we add this into solution, for example. As we go down the group, reactivity now decreases. Now, we start off very similar to our alkali metal explanation. It's because as we go down the group, the atom becomes larger and the outermost electrons are further away from the nucleus. So again, there's a weaker attraction between the outermost electrons and the nucleus. But this now makes it harder to gain the final electron to get an outermost shell that's full. And so that means that chlorine finds it harder to attract an electron than fluorine does. And so it will be less reactive. Now the halogens, again, they react in similar ways because of the fact they've got similar electron configurations. So chlorine and hydrogen, for example, will make hydrogen chloride. The halogens also react with metals. And so, for example, here, chlorine and lithium have made lithium chloride. This will be a white salt in appearance. So green gas, a silvery metal, will actually, in this case, form lithium chloride, a white solid. There's a couple of opportunities in the chemistry paper 1 where you might be asked about displacement, and the halogens is one. With this, displacement is the idea that it's a chemical reaction when an element that is more reactive than another displaces or takes the place of a less reactive element. And what that means is a chemical reaction occurs and we get a new product made. So we can use this to prove the reactivity of the halogens, and it's a typical experiment we might use. Because if we're saying that as we go down this group they're getting less reactive, well actually chlorine can displace quite a few things. Iodine cannot. So what we'll find is that halogens higher in that group can displace elements lower in that group. Let's say we've got chlorine and we add this to a solution containing another halide. What we'll find is the chlorine will displace that halide. So we'll find if we add chlorine water to potassium bromide, the chlorine water is relatively colourless, and when this reaction occurs, the chlorine will take the place of the bromide. So we'll end up with potassium chloride and bromine that's been displaced because it's less reactive. So there's the reaction that's taken place. Notice the chlorine and bromine have swapped positions. Now our observations of this is we'll end up with a colourless kind of solution, which will end up orange because that's the colour of bromine when dissolved when in solution. And so what we'll see is that actually we will see a colour change with that displaced halogen. In the final section, we're going to look at our transition metals. Now this is content that is for separate science only. Transition metals are metals, and so they do have properties in common with group 1. And we find these in the middle block of the periodic table. And there's loads of different metals in there like iron, and we've got chromium, for example, titanium, gold and silver are there too. Now generally, be prepared, you might be asked to compare the transition metals properties to group 1. Group 1 have much lower melting points than transition metals. The transition metals are much denser and they are stronger, and they are also harder. With the reactivity of oxygen, what we'll find is that group 1 is far more reactive than transition metals. The group 1 will also react much faster with water, and they'll react much faster with the halogens. So the chemical reactions of group 1 are much more vigorous. Notice they may react. Transition metals are unlikely to react with oxygen or water, and certainly slowly, but they will both react. But for the most part, group 1 will do so much faster than it will for the transition metals. You might be asked to describe the properties of transition metals, and one thing is they will form coloured compounds, and that comes back around in your paper 2 when you're looking at your chemical analysis. And iron there and copper come up a lot. Now, also, the transition elements have the tendency to form ions with different charges that we'll look at in a moment. But they are also really useful as catalysts, and they can conduct electricity really well. Remembering and recalling, for example, that we're using transition metals as catalysts does tend to get forgotten a bit more. It's only ever a little mark here or there dropped, but for example, you might be asked the use of iron within the chemical reactions. If they ever mention a transition metal involved with the chemical reaction, little alarm bell should be ringing. Maybe we're talking about a catalyst here. With the ions of different charges, there will always be a hint of this in the exam question because, for example, iron can make iron 1, iron 2, iron 3. And the Roman numerals in the sentence gives you an idea behind this. So here we've got iron with an Fe+1 charge. Now that is formed when we lose 1 electron. But if iron forms a 2+ ion, it's lost 2 electrons, while iron 3 has lost 3. So this transition metal can sometimes lose 1, lose 2, or lose 3 electrons, forming these ions of different charges.